Okay, so we continue from the previous uh, class. So where we were looking at the anagrams of the word LOOK. Okay. So did you think about the way how to count the anagrams of LOOK and why is it different from that of LOCK? And if you have solved it, very good. Otherwise, we have to wait a little more before we look at this counting. Okay, so we will look at another example now. So a family from, let's say, Maharashtra decided to go for a tour. Okay, so for their vacation. So when they were thinking about this, they decided, okay, either we can go to Kashmir or we can go to Kerala. Okay, so the either the southmost or the northmost part of India, maybe, right? And both are like very beautiful, beautiful states and very nice places to see. And then they said, okay, in Kashmir we can, we have 9 possible interesting places we found, and then out of these 9 places, maybe we can visit 4, right? With our budget, we can visit 4 of these places. Or we can go to Kerala, where we found 10 interesting places, and maybe we can go to 5 out of these places. Okay. So these are our choices. So we can either go to 4 places out of these 9 interesting locations that we shortlisted, or any of the 5 locations in Kerala out of the 10 places we have shortlisted. Now the question is that how many different itineraries we can they can come up with. Right? So finally, they have not yet decided, but suppose they are going to decide, right? It can be any of this, right? Because they don't have maybe a preference, but they or depending on their preference, they choose one of these. But which one is it, right? So what are the possible options that we have for their itinerary? So itinerary means that the order is important, right? The way that they are going to visit. Like for example, if you are visiting, let's say 3 cities, right? Going A, then to B, and then going to C is different from going to A, then to C, and then to B, or from B, A, and C, because the travel tickets and bookings of the hotels, etc., are going to be different. So the itineraries are going to be different depending on the order in which they are going to visit. Now, how do you find out the number, right? So here we are going to use 2 different principles, right? We have both the addition principle and the product rule, right? So these 2 principles we can use because, for example, if you take the first part alone, right, going to Kashmir and visit 4 out of the 9 places, right, we know how to find it, right? So out of the 9 places, I want to select the order in which I am going to visit the 4. So how do I do this? So out of the 9, I can choose any of the 4, right, places. So the first place I am going to visit, I can be any of the 9 places. The second place I am going to visit can be any of the remaining 8 places. The third place is going to be any of the 7 places. And the last place I am going to visit in Kashmir can be any of the 6 places. But they may not decide to go to Kashmir. At the end, maybe they decide, okay, we can either go to Kerala or to Kashmir, right? So maybe they, instead of the Kashmir, they have all these possibilities. And then this can be multiplied, right? Because the choices are independent. Or in the other case, they decide to go to Kerala, right? They have 5 possible destinations they can choose from the 10 possible available places, right? So 10 choices here, then 9 choices here, 8 choices here, 7 choices here, and 6 choices here. So multiply this, and you get the possible ways to visit 5 locations in Kerala. But since it could be either this or that, we can, and they are disjoint choices, we can add using the addition principle, right? So therefore, the total number of itineraries is 9 choice number, I mean, like the 9p, the permutations, right? P, how many? 4 plus 10p5, right? So this is the answer, right? Or 9 into 8 into 76 plus 10 into 9 into 8 into 76. Right? So, so this is 11 into 9 into 8 into 7 into 6. So this is the total number of itineraries they can come up with. That's a huge number of itineraries, right? Okay. Now, here is another question. So I have 8 different cowrie shells. Okay. So cowrie shells you might have seen, this kind of very beautiful, very nicely shaped small shells that you get from the sea. And they have a distinctive face, like it comes. I don't know how to draw, okay, but I'm sure that you can figure out. So there are this, or you can search in Google and find out what are cowrie shells. So look at the cowrie shell. You can see it's a distinct face, right? It has a nice rounded face and a flat face. Now, I want to make a necklace out of this cowrie shells. It used to be the fashion in the prehistoric eras. People, or even not necessarily prehistoric. Even nowadays, people started using it, but it used to be very the only things available. Before people have invented gold and things like that. So but they still you can make necklaces without using gold. So now we want to use necklace. We want to make necklace using these 8 different cowrie shells, but they are of different colors. Okay, so they come in different colors. Now, how many ways you can make this necklace? Because the order, when the way you keep can be different. It looks different, right? But we assume that the faces of the shells must all face the same way, right? I don't want to put one shell this way and the other one this way, etc., like this, or even one like this and one like this, right? That I don't want. So everything must be faced in the same fashion. So how many ways you can do this? Again, stop for a minute. Think about this question. Can we use any of the earlier used principles, or we want something new? Or maybe you need something that we already know and then something new, or like we can use many of the earlier things used here or just one of them. So whichever way, find it out. Now, suppose suppose we were using so this is the structure of a necklace, let's say, right? So you have the why is it not okay? So you have this necklace, and you can put 8 of the different cowrie shells here, right, in a particular fashion. Now they are of different colors, so the order in which you keep are going to be different. But since it is a necklace, see, let us say, suppose initially, like instead of this necklace, we had let us say that we just break the necklace by putting a connector here, right? Let's say a connector here and the corresponding a male connector here maybe, and a corresponding female connector here, right? So I can put this thing together, right, one inside the other, so that it locks. If I was doing this, then or in other words, if I am looking at a linear arrangement of the cowrie shells, right, in a line, right, so I can just open this up, it forms a straight line, right? But here is a special hook maybe, and here is another hook. So the way I'm going to put here are going to be different, right? So there are all possible permutations or linear arrangements of these 8 shells. So therefore 8 factorial ways I can do this, right? So the number of ways I can arrange in this line is going to be 8 factorial. But now, since I'm going to put this in this circular fashion, without using any of these connectors like this, then what I can say is that, see, if I take this necklace and just rotate it, right? I just rotate it this once, right? So this shell comes here, so this comes here, this comes here, this comes here, etc. So I just rotate the necklace. It is the same. No, it doesn't matter. Rotating a little bit does not make any difference. So if I rotate it, it is not going to make any difference. So therefore, if I had this 8 factorial arrangements, right, I take one of this, right, I put the into this form and then make this circular necklace. If I rotate, the thing, the cowrie shell which was here after the rotation will come here, right? After rotating, it comes here. So I get a different permutation, but it's going to give the same necklace. So therefore, 8 factorial is not the correct answer because I am overcounting some of them. Now, how many times I am overcounting? So what you can observe is that since once I take any such permutation and make a necklace, if I just rotate it like and put this guy to this position or put this guy to this position, put this guy to this position, right? So any of this will give the same necklace, or in the circular fashion, they are all going to give the same order, right? Circular order is the same. So therefore, in the necklace, they are all going to be the same. But one necklace, one cowrie shell can sit in any of these 8 different positions. Once you fix the order, and everything else will rotate together, right? And therefore, there are exactly 8 possible ways for this guy to be moved around in the circle. Therefore, out of these 8 factorial arrangements, 8 of them are going to be giving the same circular order. But now this is true for any given order, right? Any instead of this, I take some other arbitrary order, like then I do this again, the same thing. Each one corresponds to 8 cases in the linear order. So therefore, for all of them, I have exactly 8 possibilities which are giving exactly the same necklace. So therefore, I can divide by 8, right, intuitively. So I divide 8 factorial by 8. So I get 7 factorial, right? 8 equal to 8 factorial divided by 8, right? 1 into 2 into etc. up to 8 by 8 is 1 into 2 into etc. up to 7. So this tells us that the number of possible arrangements of the necklace, the cowrie shells into a necklace, is 7 factorial. And what we use here is so we use 2 principles, right? We used the product rule, and then we use something, some observation to be able to divide. Now, how did we divide? What allowed us to do the division? So let us make it precise. So let us consider 2 sets, S and T, both are finite sets, and consider a function, let's say f, which maps from T to S. Okay, we call the function f to be D to 1 function, where D is a positive integer. If for every element S, let's say in S, exactly D elements of T, D elements of the capital T, right, has f of that element is equal to S, right? Their image is going to be S for exactly T elements. So with respect to the function, exactly D inverse elements, each element in S has. Then it's called a D to 1 function. Here is an example of a 2 to 1 function to make it more clear. If you have not seen this, math students of course know this already. If you have not taken math courses, maybe you are not familiar with the terminology. So here you have one element of S and correspondingly exactly two elements, right? According to F. Similarly, for this element, I have these two elements. And for this guy, I have exactly these two. So, because the pre-image or the inverse elements of each of the element in S are going to be exactly 2, it's a 2 to 1 function. So, similarly, you define D to 1 function. Now, the division principle says that if for some function F, there is this D to there is, for some function F which maps from T to S, that function F is D to 1, then cardinality of S is equal to cardinality of T divided by D for finite sets S and T. So you have sets S and T, and if for some positive integer D, right, we have F maps from T to S is a D to 1 function, then cardinality of S is equal to cardinality of T by T. Once you see how this function behaves, it's immediately clear to us, right, intuitively. But we are going to form it as a division and say it as a division principle. And this principle can be used precisely when you can define such a D to 1 function. That is important. So here is a question. 40 students are there in a class, and 3 are going to be chosen as class monitors. Okay. Now, how many ways we can choose them? So from the previous countings that we have done, we can now see that, right, I want to choose 3 persons for the monitors. So for the first monitor, I can choose any of the 40 students, right? So there are 40 choices for the first monitor. Then for the other monitor, second guy, I don't, I am choosing 3 different people, right? So I cannot choose the first guy. So that I can choose any of the 39 remaining students. Now, once I choose the 39, the second person out of the 39, then the third person can be chosen other than the first two, right? So there are 38 choices. And these choices are independent, right? So therefore, 40 into 39 into 38 ways I can choose these 3 guys, right? Is it correct? So, if you don't think it is correct, how do you improve the answer? Or if you think it is correct, think about it again and see whether there is something that we are missing. Okay. So now the argument is incorrect because we count the same 3 persons more than once, right? For example, when you look at, let's say, persons A, B, and C, right? So the first person to be chosen as the first monitor was, let's say, A. The second person chosen was B, and the third person chosen was C. In another choice, we could have chosen, let's again, A as the first person, C as the second person, and B as the third person, and we will still get the same 3 A, B, C as the monitors, right? Similarly, I could have B as the first choice, right? C as the second choice, and A as the third choice. We will still get the 3 guys as the monitors because we didn't distinguish between the positions of the monitors, right? We just said there are exactly 3 class monitors we are going to choose. We did not say that one guy is superior to the other, or one guy has higher rank than the other. Nothing like that, right? So therefore, all these, ABC or ACB or CBA, right? Each of these choices are going to give us exactly the same 3 guys. So which means that we have counted them more. So we already did some overcounting. So now can we do something to undo the overcounting, right? So we observe that in each of the cases, we do the overcounting also exactly the same number of times. Okay? Because if ABC are going to be the monitors, it could be either of these ABC, ACB, or then what are the other choices? BCA, right? PAC, or CAB, or CBA, right? And exactly these possibilities only, right? Any other choice of any other choice of order, right? All the people will not give exactly these three guys. So therefore, to choose the three guys, we have we have counted them in how many times? 1, 2, 3, 4, 5, and 6 times. So 6 times we have overcounted the same triplet of people, right? And one can think about a little bit and see that for every triplet this is true because ABC were arbitrary, right? So therefore, we have a D21 function. If you want to define formally the sets and all, you can do it. I will skip that part, but think about it and try to define it. It would be a nice way to see. So we have this function, and therefore we can use the division principle and say that since we counted this 40, where is that? 40 into 39 into 38, and every triplet we counted exactly 6 times. I can divide by 6 now, right? So this is going to be the number of ways to choose the 3 class monitors. Okay. Now, now more generally, this same principle can be used to count the number of k element subsets of a set. So what we did precisely was to find a 3 element subset of this 40 element set, right? Because we wanted to just choose 3 persons. So that was a 3 element subset. But what we did was to basically count the 3 permutations and then we divided by 6, right? But in general, what we can do is that we can count the k permutations, okay? And once you do the count the k permutations, we observe that the k permutations of a fixed set are going to be exactly k factorial, right? And once you have any of these k factorial, they will all give the same set. So therefore, I can divide by the k factorial to get the total number of k element subsets. So to count the k element subsets, I can just use this, right? So first count the thing that we already know how to count, right? The k permutations, and then divide by k factorial. So we have the k permutations here, which is p and k, and then I divide by k factorial. So I get n factorial divided by n minus k factorial by k factorial. So, right? That's n factorial by k factorial into n minus k factorial. So this is our a number of k element subsets. So we can count the subset by counting the k permutations first, right? Or listings, right? K element subset that we can list, right? Okay. So we denote this number by this way. We have seen this many times, I am sure. Math students definitely know. So n choose k is called n choose k. You read this. So this is the standard notation to say that we are going to choose k element subsets of an n element set, right? That is the number of ways to do this. The number of k element subsets of an n element set, n choose k. Now, this number is called the binomial coefficient. Okay, kth binomial coefficient of n, and the reason is because this appears in the well-known theorem called binomial theorem. So, what is binomial theorem? So, binomial is a polynomial with exactly 2 terms. So, you have these 2 terms, and that is called a binomial. So, x plus y is a binomial. Now I take the binomial and take the nth power of it, right? So it's basically product of n copies of x plus y, right? So x plus y is its factor. There are n copies of this factor. So how do you expand this, and what are going to be the terms, right? So binomial theorem says that this expansion is precisely summation k is equal to 0 to n choose k, x raised to k into y raised to n minus k. So what we know is that when you take the product, you can only have as factors either terms coming from the monomials coming from x and y, right? Every factor must contribute one of the factors x or y. So it will be some power of x and into some power of y, right? These are going to be the terms. All the terms are going to be this way. So it can be x raised to 0, y raised to n, right? Or x raised to n, y raised to 0, or x square and y raised to n minus 2, or any of these things. Now, how many of these guys are there, right? So to basically, so if you want to write, there is going to be like many terms coming here, right? So we don't want that. So we want to write them together. All the similar terms I can put together. But how many of them are there? So binomial theorem says that precisely n choose k terms of the form x raised to k, y raised to n minus k are going to be there. Why is this? Well, this is immediate actually. If you look at the product x plus y whole raised to n. So what is x plus y whole raised to n? It is x plus y into x plus y into etc. x plus y, right? Now, how do I form the term x raised to k, y raised to n minus k? To form x raised to k, y raised to n minus k, I should be able to choose exactly k copies of x, and the remaining all must be copies of y, right? Because I don't have a choice but to choose from every factor at least once, right? Because the product has all these n terms, they are multiplying. So from each of this, I have to choose one, right? So how many ways I can choose x raised to k? The remaining must be all y. So there is no choice, right? So if I choose k of the x's, then I am done. So how many ways I can choose k x's? Well, so we have exactly n right factors, right? X plus y, the first copy, second copy, etc., nth copy. So out of these n copies, I decide which of the k copies I want to select the x from. So how many ways I can do this? Exactly n choose k ways. So the n choose k ways I choose x raised to k. The remaining all terms I don't choose, right? Whatever is except for this set, everything else, the complement, all the n minus k sets are going to give exactly y, because otherwise the power of x will increase, right? So therefore, by definition of n choose k, we can see immediately that this is coefficient of x raised to k, y raised to n minus k is exactly n choose k. Now, how many terms can appear? Well, k can be either 0 or 1 or 2 or up to n. So therefore, x raised to k, y raised to n minus k, summation k equal to 0 to n choose k. That is the expansion of x plus y whole raised to n. So that is the binomial theorem.